constructing exponential functions. This is out of your text. 15.3 is the lesson. Your essential question, what are discrete exponential functions and how do you represent them? Our learning goal today is I can construct exponential functions using geometric sequences from verbal descriptions. So we're taking what we know about geometric sequences and we're applying that to exponential functions. A little bit of review, okay? If we look at a geometric sequence, and this is the same one from our poll question this morning. So here's the sequence, 125, 25, 5. That's the one I gave you, and I asked you for the common ratio. And it's showing here that if I multiply 125 by 1/5, I get 25. If I multiply 25 by 1/5, I get 5. And this pattern continues for the sequence. Since the pattern is multiplying a constant number each time, this sequence is geometric. Since the terms are decreasing, the common ratio is a fraction, essentially dividing. Remember, multiplication and division, those go with geometric sequences. Addition and subtraction goes with arithmetic sequences. The common ratio can also be found by dividing any term by the term before it. So like I said, you had two choices. You could either do 25 divided by 125 and simplify it to get 1/5, or you could divide 5 by 25 and get 1/5 as well when you simplify. You just pick two terms that are next to each other. If there was more terms here shown, you could pick any two that are next to each other, but you're always going to get 1/5. And so just overall, this is a geometric sequence and the common ratio is equal to 1/5. Some vocabulary for this new unit. When we talk about a discrete function, that is a function has a graph consisting of isolated points and not a continuous curve or line. This picture right here is an example of a discrete function. It is just points. We are not connecting the dots. A discrete function, do not connect the dots. It's isolated points. Exponential function, a function whose successive output values are related by a constant ratio. Okay, so if you have something where the outputs, all these values are all related by a constant ratio, that's kind of like the common ratio, just like in a geometric sequence. It's essentially one and the same. But we call this an exponential function when we graph it. And this is actually a picture of an exponential function right here. The relationship between the outputs. The outputs are the y values. The inputs are the x values. Or as we saw with sequences, we were using n when n equals 1, when n equals 2, when n equals 3. And then we would get the sequence terms, just like the outputs are the y coordinates for these points. Anytime you write an exponential function, we can represent it by an equation of this form right here. So this is like they call it the parent form. F of x is equal to a times b dx power. This should look somewhat familiar if you think about our sequence rules where we had a sub n or f of n, and we had the first term in the sequence multiplied by the common ratio raised to a certain power. So it's following that same basic pattern. Okay, a number times another number raised to a power. All these values, a, b, and x, they're all real numbers. Okay, what that means is none of them are imaginary. A does not equal 0, b is greater than 0, and b is also not equal to 1. All right, so if these are true about the values here, then this is an exponential function. Or an exponential function f of x. If x is the domain of the function, then the ratio of f of x plus 1 to f of x is a constant ratio. This is just like when we were trying to find the common ratio, where you would take a term and the next term and then divide. That's basically what they are saying right here. Okay, f of x plus 1 and f of x, those are two outputs next to each other, And then if we do the same thing where we divide them, that's your constant ratio. Before we were calling it a common ratio, but it's always the same number, so it's constantly that ratio. Okay, so this is a slide that we're going to work on together. And up here, we have the actual exponential function. F of x is equal to 3 times 1/2 x. And the domain for this exponential function is -1, 0, 1, 2, 3, 4, close the set. That's it. There's only 1, 2, 3, 4, 5, 6 inputs for this function f of x. And so we're going to create a table here where we already have all the inputs listed. These are the same x values that are in this set. We're going to plug each x value into the function and get the output and put it here. And then by putting the input with the output, we'll have an ordered pair. And then we'll be able to come over here and graph all 6 ordered pairs to graph the exponential function. Now, this is a discrete function because it is a closed set of specific isolated points. We're not going to connect the dots. It is an exponential function because it is of the form f of x equals a times b to the x power. Okay, a is 3, b is 1/2, x is x. So we're going to take turns plugging in these values to see what we get. The first one is already done for you. For x equals -1. X equals -1, you replace the x with -1, and then you write out the function and replace the x with -1 again. Now, as we simplify these, you have to remember all your exponent rules. All right, so it's not just like a simple function like f of x equals 3x. You have something where x is actually the exponent. So we have to remember what we do when you have something raised to the negative power. This is one of our previous lessons. What you do is you take the base of 1/2 and you move it to the denominator and you make the power positive. So I'm going to come over to this slide and get my pencil tool here. And I am going to draw in. You can do this too, because they're not very much showing you this step, but to go from right here to right here, the 3 stays the same, okay? But this power, 1/2 to -1 power, becomes 1 over 1/2 to the positive 1 power. And they didn't write the positive 1 here because when 1 is your exponent, we typically don't write it, but that's what happened. Okay, so this is the rule about negative exponents. Now what we have is 3 times 1 divided by 1/2. Right, 1 divided by 1/2. Let me just show you, in case you don't believe me. Here's a calculator. 1 divided by 1/2. 1 divided by 1/2 is the same as 0.5, right? Equals 2. That's why this turned into 2. And then the last step, 3 times 2 is 6. So when x is -1, f of x is 6. I'm actually going to use the typing tool. And I am going to suggest that you use the typing tool because it keeps it not so messy, right? How did the number rise? Which number? Which number are you referring to?
How did 1 over 1/2 turn into 2? Because isn't fraction mean you're dividing?
Okay, so what happened is, let me use like a highlighter tool. So we have the 3 here, which is still this 3 here, which is still this 3 here. That 3 never changed. The thing that was changing was 1/2 to the -1 power. So the rule for a negative exponent is you take the base and you move it to the denominator and you change the sign of the exponent to a positive, and then you can put a 1 in the numerator. So this is a rule that we have, and I'll show you where it's at. It is back in, I want to say week 6. I think so. So you can always go back to any of our older pair decks, which is what I'm going to do right now. I'm looking for, here it is. So when we talked about, when we started learning about radicals and exponents, here's that rule. Any non-zero number raised to a negative power is equal to 1 divided by the same number raised to the opposite positive power. So here's an example of 3 to the negative 2 power. The 3 goes to the denominator, the negative 2 becomes positive 2, and a 1 goes in the numerator. So it's a really good question, and it's just about remembering these rules. So we are going to be referencing the 0 power rule and the negative power rules today, working with these new problems. Okay, so that's how we went from here to here in blue, because this is just a negative power rule. 1/2 to the 1 power, or 1 divided by 1/2 is 2, and then 3 times 2 is 6. Does that help a little bit? I think as you work with these, like the negative exponent rule is not real intuitive, right? Because I don't know, I just don't think it is. But we're gonna do this next one, and it's a lot more intuitive. Okay, so now we're gonna look at when x is 0. Okay, when x is 0, and I'm just gonna come over here and show the work because I don't really have a lot of room up here to keep doing this. But we're gonna substitute into f of x, right? So f, and replace the x with 0, and that's equal to 3 times 1/2 to the 0 power. Okay, so you see what I did is I took the next value for x, which is 0. I'm using this, I'm using this is the formula here that we're going to keep using over and over again. This is our exponential function. And so I plugged it in and just replacing the x with 0 now, instead of replacing it with -1 like we did for f of -1. Right here, this step, anything to the 0 power, and this is coming back to these two rules here, any non-zero raised to the power of 0 is 1. This is defined to be this. So anytime you have something raised to the 0 power, we change it to being equal to 1. So this actually becomes 3 times 1. 1/2 to the 0 power is what? 3 times 1 is just 3. So when x is 0, f of x is 3. Was that one a little bit easier to follow than the negative exponent? And then we're just taking our x and our f of x and putting it into a form that I can plot. We're going to keep doing this with the different x values. So now we're going to look at x equals 1. So f of 1 is equal to 3 times 1/2 to the first power. Anything to the first power is always itself. So for each of these, we're using these different exponent rules. That's why we were working with exponent rules and radical rules this past week, because we have to remember them or essentially learn them and use them depending on if you learned them or not in 8th grade. Okay, so the negative exponent rule, the 0 exponent rule, anything to the first power, that's not one you would have learned in 8th grade. That's kind of when you learned about exponents and powers. So in middle school, in general, anything to the first power is always itself. So 3 times 1/2 to the first power is the same as 3 times 1/2. And 3 times 1/2. If you want to use the calculator, you can. 1/2 is 0.5. So 3 times 1/2 is 1.5. And you can write your answer as a fraction, or you can write it as a decimal. Okay, either way is okay. I'm going to put it as a decimal because I think maybe that's a little bit easier to graph when we're looking at graphing. But either way is correct. And so now that I know that x is 1, f of x is 1 and 5/10, that's going to be my ordered pair that I'm going to plot. Okay, and I can even start plotting these over here, right? I get I resize my pencil tool, and I'm going to first plot 6 when x is -1 and f of x is 6. This point right here, -1, 6. Okay, so if I go to -1, and then I go up to +6, this is where my first point is. I actually want to do that in blue, so you can see where that came from. -1, 6. My next point, I'm going to do in purple. So 0, 3. Here's 0. Here's 3. My next point. My next point, 1 and 1.5. So I go to +1, and then I rise to 1.5. All right. And just by having 3 points, you can already see these are not going to, it's not a linear, it's not a straight line. Okay. The distance between the blue and the purple and the distance between the purple and the pink are different. The distance is shortening. It's going to keep shortening. All right. So as we do these next points, you're going to see that. So after this, we have x is 2. So f2 equals 3 times 1/2. And that's equal to, I got to put in my little exponent here. So since x is 2, I'm going to put a 2 right here. All right. Now this 2 only goes with the 1/2. It's not the entire thing. You don't want to multiply 3 and 1/2 and then take care of the exponent, because you got to think about PEMDAS order. PEMDAS order tells me that I have to take care of exponents before I do any multiplication. So I have to take care of 1/2 squared. What is 1/2 squared? You guys know? 1/2 squared is 1/2 times 1/2. What's 1/2 times 1/2? Someone can put it in the chat. 1/4. Yeah. So 1/2 times 1/2 is 1/4, which means this is the same as 3 times 1/4. 3 times 1/4, 3/4. So right here, I could put the fraction 3/4, or I could write the decimal version of that, which is 0.75. Okay, it's the same thing. Now up here, I could do this too on this one. 1.5 is the same as 3/2. Just to show you that you can write it as a fraction or you can write it as a decimal, okay? So you can choose how you want to do that. But my next ordered pair here is 2 is the x-coordinate, and then we have 0.75 as the y-coordinate. All right, and so this is what we're going to plot next. Get my plotting pencil to make the dot a little bit bigger. Okay, we're going to go over to x equals 2, and then we're going to go up to 0.75, or 3/4, which is below 1, right? Not there. Sorry. It's below 1, about halfway between, right here. And again, my distance is getting shorter and shorter between these points. And that's going to continue because it's an exponential function. Right, so number 3, I'm going to keep moving here. F of 3 is 3 times 1/2, and that is raised to the power of 3. See, this is my x that keeps getting replaced with whatever I'm plugging into the function. So a 3 right here. 1/2 to the 3rd power is 1/2 times 1/2 times 1/2. What is 1/2 to the 3rd power? Mauricio has it. 1 times 1 times 1 is 1, and 2 times 2 times 2 is 8. Okay, 3 times 1/8 is 3/8. 3/8. You know, if I want to put that as a decimal, I don't have that one memorized. I'm going to do 3 divided by 8, and that's 0.375. All right. You don't have to write your answer 2 different ways each time. I'm just doing that to give you more information to help you understand how these values are getting smaller exponentially. All right, and so my ordered pair here, if x is 3, and then y, or f of x, is 0.375. And then I'm going to plot this point. So I go over to +3, and then I'm going to go up 0.375. So that's less than halfway up. So notice these points are getting closer and closer and closer to the x-axis. They're never going to pass the x-axis, but we're going to keep getting closer and closer to the value of f of x is going to get closer and closer to 0. All right, and then there's one more. F of 4 is equal to, and I'm going to show you Desmos too before we're done with this, because Desmos is going to be really helpful because we're doing this the long, hard way by hand. Desmos is really nice because Desmos is a graphing calculator, and it's going to show us the same picture that we have here that I have graphed. So f of 4 is the same as 3 times 1/2 to the 4th power now, which is the same as 3 times 1/2 to the 4th power. is 1/2 times 1/2 times 1/2 times 1/2. 1 times 1 times 1 times 1, 4 of them. That's just 1 in the numerator. And the denominator, 2 to the 4th power. 2 times 2 times 2 times 2. What is 2 to the 4th power equal to? $16. 2 times 2 is 4, times 2 is 8, times 2 is 16. Okay, so 3 times 1/16. I come over here, this is the same thing as 3/16. 4 as a decimal, 3 divided by 16. Again, we're getting closer and closer to 0. These numbers are getting smaller and smaller. All right, and so the last ordered pair, 4 and at long decimal there. So it's probably, you know, at this point, maybe it's easier to leave it as a fraction. I don't know. It's less writing. 3/16 is less to write than this decimal. But either way, it's the same value. We're going to plot this last point, 4. So I go to positive 4. And again, I'm still above the x-axis, but not very much. I'm getting very close to 0. And it's hard to even graph that accurately. Okay. As you keep doing more and more points, it's going to continue out this way, but we don't have more points. This is it, because this is a an example of a, here, let me go back. This is an example of a discrete exponential function, right? This is a discrete exponential function. Okay. Let's kind of clarify what this is. That's our vocabulary. That's what this is. Now, I do want to show you that I'm going to open up our good friend Desmos. See our good friend. He's my good friend, whatever that means. And I lost my screen. There we go. The Desmos graphing calculator. If you don't have this bookmarked on your like web browser, you could add it, or just go to desmos.com/calculator. Now, if I just type in this function, it's going to give me a different graph. I want to show you this. So if I type in f of x equals 3 times 1/2, and then I raise this all to the x power. In order to get an x exponent, I have to open up the keyboard and then use this a to the b power and then type x. If I do that, this is the picture I get, which follows this pattern, but it's a line, it's a curve. Excuse me, it's a curve. The reason why it's different than what I have is because my domain is different. So by just typing in this, this is saying the entire, all the real numbers are my domain, but it's not. It's just these values here, okay? So instead of doing that, maybe I'm going to add a table, okay? So if you're working this out and you can get your table, or you can type in the function just to get an idea of where things would be, you can use Desmos to help you. If I just type in these values, okay, so for x we have -1, for y I have 6, and then for x equals 0, I have y equals 3. For x equals 1, I have x is equal to, I'm sorry, y is equal to 3/2. You know, I could type 3/2. It understands fractions. For x equals 2, I could type in 3/4. or x equals 3, y would then be 3/8, or x equals 4, and y would be 3/16. And you can see now this graph is exactly what I have here. Okay, so this is one way to check your work to make sure that you're doing your work correctly. You can put in the parent function to see if you are, doing your work correctly. But depending on your domain, you may or may not have what we call a discrete exponential function, or you might just have an exponential function where all the points are connected. It depends on your domain if you connect the dots or not. If your domain is limited to specific values of x, you wouldn't connect the dots. When it is all real numbers for your domain, then you would connect the dots. And so just to show you this right here, this function, this is the parent function, and it does pass through all these points. So that shows me that I did all my calculations correctly because all these points are falling on the parent function, f of x. But because of the domain, I have to take that away. It's only these points. It's not the red line. All right. So that's the end of the lesson.